right, up next we have a question about defining u. In this question, the idea is usually u is going to be the function that is either just containing a higher power, or it's a function that if you derive it, you can see its derivative or a form of its derivative, maybe not the same coefficient out front, but the same structure. Now again, in this question, when you derive the inside, the one that has the higher power, you would get negative 12x minus 1, and that's what you see elsewhere in the problem. So what you're going to choose to be u is strictly the inside of the root. Now, in other words, one thing you want to kind of keep in mind is that u substitution is happening when the chain rule is present in your problem. In other words, you have one type of function you would derive inside of another type of function you would derive. So when you have these functions inside of functions, or the same thing as saying a function you would integrate or inside a function you would integrate, when you have a type of function inside another type of function, in other words, a polynomial with a radical function, that's your kind of idea that u substitution is going on. Same thing if there was a polynomial inside of trig or things like that. All right, up next, just again, another basic definite integral. And this one I'm going to still get a little bit faster. If I increase the power by 1, there would be x squared, and I have to offset that with a 2, but the 3 is still up front. Now I have 3x, and I'm evaluating this from 5 to 10. Here is we're going to get 3 over 2 times 100 plus 30, and then that's going to be minus, and really all I did there was I just plugged in 10, and then I'm going to plug in 5, which will be 3 over 2 times 25 plus 15. All right, now from there, let's see here, this is actually going to be 150, so this is 150, that'll make this 180, and then be careful, it's 180 minus that 15, so I have 180 minus 15, and that's 165, and then I still have the negative, this will be 75 over 2, so I need to get a common denominator of 2, that's going to be 330 over 2 minus 75 over 2, and that's going to be 255 over 2. There we go. Got that wrong more times than I wanted to. All right, up next, we've got this is really a fundamental theorem of calculus question. And this is a topic that's super important for the AP exam as well. I would definitely assume this is going to show up on an FRQ, so definitely pay attention to this. You have g of x, and the key to this problem is noticing that x is a bound of integration. So in other words, you need to integrate this whole thing and then substitute x and then substitute 0, and x can be whatever you want. But from there, the idea is the other structure is really a function of t in dt. And the idea is after you substituted x's and you've substituted zeros, whenever you substitute an x, that's going to be a new function. Whenever you've substituted 0, that's going to be some constant. So when you derive whatever this integral is, there's now some higher function with x's, and when you rederive it, it's just going to go back to the structure that you had before, but with x instead, because the t was replaced by an x. And now that we have this new structure, now that we have g prime of x, we can now substitute in pi over 4. You substitute in pi over 4, tangent of pi over 4. Remember at pi over 4, that's the root 2 over 2 and root 2 over 2, so when you divide the y value by the x value, this is going to be 1 at pi over 4, so we now have 5 plus 4 times 1, so we have the root of 9, so we just have 3. All right, up next we've got another fundamental theorem of calculus question going on here. And so the idea is we want to know why g has an inflection point, and so if we want to talk about inflection points, we have to talk about second derivatives. So we want g's second derivative. Well, first let's look at what g's first derivative is. Because of the fundamental theorem of calculus, if you were to derive g on the left, what you would get on the right is just f of x. And then if we want g's second derivative, well, what did we do here on the left? We just derived g. So how am I going to go from here to here? Well, I'm just going to derive f. So if I want to know what's happening with g's second derivative, then I really need to know what's happening with f's first derivative. And so here is the graph of f. Its first derivative is the slope, and if you look at this, the slope is going from decreasing to increasing, or in other words, from negative to positive, is more so what I should say. And so since f goes from negative slope to positive slope, in other words, because f prime changes signs, g double prime changes signs also at c, and that doesn't sound right. Oh, because f is a relative minimum at c. That's another way of saying essentially f is changing from decreasing to increasing. Really fancy, tricky question there. All right. Next, this is just a basic integral question. I'm not really going to go through this too much. Again, just kick out the negative 36. The question is, what do you get cosine from? If cosine was the derivative, where did it come from? And it came from sine. So we have sine, and we need the negative 36 that was tagging along, and that's it. All right, this is again a fundamental theorem of calculus question, but this time notice the upper bound isn't just simply x, so it almost works itself out the same. Usually what you've gotten familiar with is you're just replacing t wherever, or you're replacing t with whatever that top bound is. So that's still true. I'm replacing t with x squared, but just remember that there was also a squared from before. And then in the denominator, same idea. We have x squared, but it was squared plus 1. So you can just see I've only been replacing the t's with what's here. And there's one last step when this isn't just a simple x. It's actually been happening invisibly. You also need to multiply by the derivative of this top bound, which means you're multiplying by 2x. So when it's just x, when you derive that, you just get 1. So you're just multiplying the replacement of x, the whole structure, by 1. But this time, it wasn't just x, so we have to multiply by that whole derivative of the top value. Again, you could also simplify this to be x to the fourth over x to the fourth plus 1 times 2x, and you could maybe do some other simplifying, but I'm just going the easy route for now. All right, now we've got some more what I'll call basic integrals. Again, the idea is you first need to increase the power by 1, which means now it's just to the negative first. And the question is, when you drop negative 1 down, what needs to be here so that you don't see anything up front? And the answer is just an extra negative so that it just reads positive whatever x is to its new power, which would be to the negative second. All right, now we have to do a trapezoidal sum. There are lots of ways of doing a trapezoidal sum, but I'm going to do it the most basic way. And the most basic way is 1/2 times the gap in x, how far it moved, your step length, and those are always in terms of x, and the step length here is 3. You go from 0 to 3. And then that's 1/2 times the height, and a trapezoid is then base 1 plus base 2. All right, so in other words, when you do Riemann sums with trapezoids, the height is actually the change in x. So this first trapezoid goes from 0 to 3, so the height is 3. And the actual bases are the y values of the function. But we're not done yet. We need 3 trapezoids. So our next one, still 1/2 times the height, which is 3, times base 1 plus base 2, which this time is 6 plus 3. Do that again. Now we have 3 plus 4. All right, now we have, this is 14 times 1/2 would be 7 times 3 is 21. And then we have 9 times 3 is 27 over 2. And then we have 7 times 3 is 21 over 2. 27 and 21 over 2 actually make 48 over 2, and 48 over 2 is 24. So 21 plus 24 is 45. Yay. All right, now we have to actually write the correct equation of a right Riemann sum. And a right Riemann sum, here is the key here. We actually count how many summations we need in terms of how many we want. So since we want 4 equal subintervals, we need to count either from 0 to 3 or from 1 to 4. And we count from 0 to 3 when it's a left interval, which we don't want, and we count from 1 to 4 when it's a right interval, just by convention. So it has to be one of these two. You'll never count like this in a Riemann sum anywhere in this course. So now the question is, which one actually gives you the correct values? And the correct values that we need for this right-hand Riemann sum is we need the height at 0. Notice the height at 0 gets carried through. And we need the height at 1, it gets carried through. We need the height at 2, it gets carried through. And we need the height at 3. So in other words, we need to, from our inputs, see the value 4, the y value, 5, 6, and 7. So which one of these, when we start plugging stuff in, do we really end up seeing 4, 5, 6, and 7, and ultimately that times the step length, which is 1. And the short answer is this one. All right, when you plug in 1, what you end up getting here is 7, that first value. When you plug in 2, you end up getting 6, which is that second value for the rectangle. And all of these, there's technically a big parentheses times 1, because that's what the step length is. You just don't see it in this example. All right. Which of the limits is equivalent to the definite integral? The key to this question is that the definition of a definite integral looks like this. For some reason, by convention, we use the right Riemann sum. Actually, I know why. It actually makes it easier to see what's going on in the function. The general idea is a right Riemann sum, or a definite integral, looks like the function of a plus delta xi times delta xi. Now, delta x in this problem is b minus a divided by how many steps you want. So b is the top value, right? Delta x is e, the top value that we want to integrate to, minus 1, the bottom value we want to integrate to, divided by n. All right, so already that kind of makes it look like, unless they've simplified this, we might be looking at C or D. Actually, definitely C or D, because when we look at the outside, that has the correct step length. This doesn't have the correct step length multiplying on the outside, so those two are out. The question is, where do you see a plus delta xi? And a, again, is that bottom value. A is 1, and so this is the correct answer. I see a plus I times delta x, or in other words, a plus delta xi. Once again, we've got a fundamental theorem of calculus idea going on here. If we want g of -1, it's not quite fundamental theorem of calculus, but it really means find the area of f from -3 to -1. So I'm just going to say that verbally. If g of -1 is what we want, you're plugging -1 in here. So in other words, you're finding the area under f's curve from -3 to 1. So we're just going to do some geometry here. We've got a trapezoid, and actually that's it. We just have a trapezoid. Actually, there's a few other ways we could think about it, but we'll do the trapezoid first. We'll do this quickly. The first height is 3, the second height is 2, or actually, yeah, heights, but really those are the bases. The step is 2, and we have to multiply this all by half. So it looks like what we're going to end up with is just 5. That's going to be our answer. Another way to think about this is notice that we're counting by 1 and 1, so this is totally good to do. We've got 1, 2, 3, 4 blocks underneath this segment. And if you were to take this little triangle and fold it back up here, you'd now have a 5th block, so getting 5 that way as well. Just make sure you're counting by 1, or you're taking into account what you're counting by if that's your approach. Ooh, the ugly ones. All right, this is a completing the square question, so I've got a lot of work to do here. What I'm just going to do is I'm going to focus on completing the square on the inside of that whole structure. I'm not going to write the whole integral, just complete the square on the inside. First thing I'm going to do is factor out the negative. And I'm actually going to leave a plus 21 on the outside. So if I redistribute this negative, I'd be good to go. This is how I complete the square. There's many ways to complete the square, but this is just my recommendation. So from there, now I'm going to introduce that blank to complete this parentheses square. I've got my plus 21, and I also need another blank to offset what I just created in here. So this question is going to get a little complex, and we'll see what we need to fill this out with. But completing the square, once you have your blanks, you divide this value by 2, and you square it. And then we need to offset what we just made here with something on the outside. And so I kind of looked ahead. There's a reason I put a plus here. Usually I'd put a minus, and that's because I technically put 4 in parentheses, but really think about what I added to this whole expression. I really added -4. How do I offset magically creating -4? Also add a +4. All right, so really I haven't added anything in terms of what this is equivalent to, but it looks totally different. Now I can write this as -x plus 2 squared plus 25. And the idea is you're actually going to see this written in like positive and the negative order, or usually the x goes second. So now I'm ready to rewrite my integral. It's the integral of 1 divided by big square root 25 minus this quadratic structure, or this completed square. Now when you look at your reference sheet, this is where arcsine comes from. Actually, I'm probably going to have to look at my sheet because it's been a while.